easiest to see, there we go, this is probably easiest to see with an actual example. So if I start with 3 and I'm doubling each time, and so on and so forth. If I want to find a formula for this, and a formula is for a general term somewhere down here, we look for a pattern. And we've already seen this pattern in the example we did before. To get from 3 to 6, I multiply by 2 once. To get from 6 to 12, I multiply by 2 again. How could I get from 3 to 12? Multiply by 4. How could I get from 3 to 24? I'd have to multiply by 2 again, which is 2 times 2 times 2, multiply by 8. And if I want to find any term, does it make sense that any term in this sequence, you would take your first term, which is 3, and how many times would I multiply by 2? Well, if I want to find the 5th term, I multiply by 2 4 times. If I want to find the 8th term, I would multiply by 2 7 times. If I want to find the nth term, I'd multiply by 2 n minus 1 times. So the formula that shows up in your formula book and the formula that is right here says, well, if I have any geometric sequence, what was the 3? 3 was my first term. What was the 2? 2 was my common ratio, how much I was multiplying by each time to the exponent of n minus 1. So we have a formula for arithmetic sequences, and now we have a formula for geometric sequences. And we can use this formula in example 3. So let's do the one off to the side. In a finite geometric sequence, the first term is 7, and the 5th term is 567. We want to find what term 2 is and what term 6 is. So what do we know? We know we start with 7, then we have something 2, 3, 4, and then we end up with 567. We can use our formula to figure this out. We know there's some sort of common ratio that we multiply by each time. We know term 1, and we know term 5. Our formula, Tn equals T1 r to the exponent of n minus 1, we can plug a bunch of information into here. What is the thing I don't know? I don't know how much I'm multiplying by. I don't know what r is. I don't know Tn unless n is 5. So if I put in T5, I can write 567 in here. I know term 1 is 7. And if I use term 5, then 5 minus 1 becomes 4. 567 divided by 7 is 81. How do you get rid of that 4? Square root would get rid of a 2. Fourth root. Fourth root. Close. So you can fourth root on both sides. Does anyone know what number to the power of 4 is equal to 81? 3. Anybody know another number that to the exponent of 4 is equal to 81? Negative 3. So the answer here could be positive or negative 3. So when we're finding term 2, can you see that term 2 could be 21 or negative 21. And if I multiply 567 times 3, the next one could be 1701 or negative 1701. The last term is 45,927. How many terms are in this sequence? So in part B here, we still know term 1 is 7. We have now figured out that R is plus or minus 3. And we want to figure out how many terms are in the sequence. So our formula just like in arithmetic sequences, this Tn stands for a general term, but there's lots of questions where we think of it as the last term. So if the last term is 45,927, I can plug that in, 45,927 for Tn. I still know that term 1 is 7. I now know that R is plus or minus 3. I'll choose plus 3 right now. And the exponent is n minus 1.
I won't do this anymore.
Okay, it's not a problem.
I'm sorry.
So, solving for this, I can divide both sides by 7. And I get 65, 61 equals 3 to the n minus 1. And unfortunately, you won't learn an algebraic way to solve this until next year. So the best you can do is check if 65, 61 is a power of 3. How would you do that? You would take a guess. 3 to the 5. Nope, not big enough.
3 to the
3 to the 8? Yes. Nice. How long did it take us to find it? Not too long. So what we can do next in our question is say 65, 61 we figured out was 3 to the 8. And this side is 3 to the n minus 1. Does anybody have an idea what n has to be? 9. Nice? You see it? Just by observation, if the one side is 3 to the 8 and the other side is 3 to the something minus 1 and they're equal, n has to be 9. 8, 9, and 11.